So for this lesson, we'll be taking a look at the idea of solving trigonometric equations, but now we're going to concentrate on examples that deal with factoring. Okay, so let's get started. Let's take a look at example one. Before we look at the example, let's actually see what we're doing. So for the following examples, we're going to try to solve the equation, and we're only going to take a look at values that are between 0 and 2 pi. All right. So the same idea that we used for the other examples hold true. So the first thing that we want to do for any examples of this form is to let's set the equation equal to 0. So to set the equation equal to 0, let's subtract the cotangent on both sides. That way this cancels out. So now we're going to have the following expression: cotangent of x times the cosine of x squared minus 2 cotangent of x equal to 0. So again, the way that you want to think about this is, notice that we have two big terms. This is my first term. This is my second term. The first and the second term has a cotangent in common, so we can factor that out. So if we factor a cotangent, what are we going to have left? We factor the cotangent. If I factor a cotangent in my first expression, what is going to be left is just cosine squared. And if I factor a cotangent on my second term, it's just going to be a 2 left. And again, when you have two terms and they're all multiplying and they're both multiplying and they're equal to 0, I can set each term equal to 0. All right, and now I can just treat them separately. But again, take a look at the left-hand side. We want to find out an angle that if I evaluate it by cotangent, it gets me 0. But recall that cotangent, this is nothing more than cosine over sine. So it is sufficient to just take a look at under what angles is the cosine equivalent to 0. So if we take a look at a unit circle, where is that at? Here it is. If we take a look at a unit circle now, at 90 degrees, my cosine it's equivalent to 0. So therefore, I have one solution coming out of this. Let me just erase this. Yes, so we know that x can be pi over 2, because notice if I take the cosine of pi over 2, that's 0, and also 3 pi over 2, which is equivalent to 0 as well. So from the first equation, I have two possible solutions. And if I take a look at the right-hand side, same idea. Let me isolate the function. So let me add a 2. So now I have the cosine square is equal to 2. I want to isolate the cosine, so therefore I need to take a square root. So now I have that cosine of x is equal to plus or minus square root of 2. But here, notice that square root of 2, the value square root of 2, it's approximately 1.41. So pretty much, we're looking for a value, or we're looking for an angle that if I evaluate the cosine function, that's equivalent to 1.41 approximately. But notice that that's not okay, because if we recall our function for cosine, the amplitude for cosine, it is 1. So the highest value that I can get is 1, and the lowest value that I can get is negative 1. But we're looking for a output that is 1.41, which is away, it's not on the same function. It is even beyond what the function can reach. So for this function, for x, there is no solution. So if we put it all together, I know for my first function, I got two solutions, and for my second function, I have no solutions. So I would put it all together. X, it's only going to have a values of pi over 2 and 3 pi over 2. So let's take a look at example B now. And again, the technique that we'll be using is factoring. So I can see that on On example B, I have three terms, 1, 2, 3. The equation is already equivalent to 0, so we're good. So what are we going to do? We want to see if we can factor anything out. No, actually, that's my mistake. We don't really want to factor it out yet so far, right away. But because I can see that I have three terms. And let's actually put this problem on the side for a second, and let's think about this. How will we go about solving How will we go about solving an equation of this form 2x squared minus x minus 1 equivalent to 0? So notice that this is a trinomial. And actually, we can factor this trinomial in the form of 2x plus 1 times x minus 1. Right? 2x times x, that's 2x squared, minus 2x plus x minus 1. That's definitely what we do have here. So notice that we were able to factor out a trinomial the way that we have done it in our previous classes from either Algebra 2 or Algebra 1. So perhaps we can think about this problem the same way, but now notice that the only difference between this problem and what we've been given is that the problem in here, we're only dealing with x's, which in this case, we're dealing with signs. So perhaps it is still a trinomial, and I know that I can factor out this way. So perhaps I can think about this problem and think about it as a factoring. So I can take a look at this trinomial and I can factor it out as 2 sine of x plus 1, which notice that it's essentially the same first factor. If it would have been an x, but instead of an x, we're dealing with the sine, times sine minus 1. So notice that we were able to factor it out. And the reason why you wanted to think about it this way, because this is a trinomial. You got three terms, you have a second exponent, second, first one. So we can definitely think about it as if it was a trinomial. And you can do this yourself. I mean, if you multiply 2 sine of x times sine of x, if you distribute this first term and you distribute the second term, you would have gotten the initial expression. But now the benefit is that now that we have it in factor form, we can just solve for it individually because I have two factors which are multiplied and they're equal to 0. Then now I can just get each factor and set it equal to 0. I got my first factor and I set equal to 0. I got my second factor and I set equal to 0. And now we can just solve for it individually. So let's solve the equation on the left. Take it with a 1 because we want to isolate the function. So now we got 2 sine of x is equivalent to 1/2. Let's isolate the sine. So divided by 2. So now we have sine of x is equivalent to 1/2. And now we stop here for a second and we think about what values of x's can I use that if I value it by the sine function, it gets me negative 1/2. But notice that negative 1/2 is one of those values in a unit circle. So let's see where in our unit circle, under what degrees in a unit circle is the sine equivalent to negative 1/2. So notice that we would have one right here. The sine of 210 is negative 1/2. So I know that one of my solutions is 7 pi over 6. And is there anywhere else where my sine is equivalent to 1/2? Well, we have it right here. Also at 330, because notice that at 330, the sine, it is still negative 1/2, which I'm going to write as 11 pi over 6. So for my first function, I got two solutions. So now, if we take a look at the function on the right-hand side, same idea. Now that it's equivalent to 0, let me isolate the function. So let me add a 1 to it. And now, if we want to look at a unit circle, where in our unit circle is the sine function equivalent to 1? But recall that sine is y. So where is my y equivalent to 1? So that will be at pi over 2. And that's actually the only place where my sine function is equivalent to 1. So in conclusion, my solutions are that x can take three values. 7 pi over 6, 11 pi over 6, and pi over 2. Let's take a look at two more problems. Let's take a look at two more problems here real quick. Same idea. Well, the first thing you want to ask yourself is my equation equal to 0? Which is not, so let's make it equal to 0. So let's add a 3 tangent to it. 3 tangent of x, and I'm going to add it underneath the other tangent of x, because I can combine like terms. So now I have tangent of x times the sine of x, negative 4 tangents plus 3 tangents, that's equivalent to negative 1 tangent. And I notice that we have it in a form that we have seen examples of in the past, because now we have two terms and they both have a tangent in common. So perhaps I can factor the tangent. And if I factor out the tangent on my first term, what is going to be remaining is just a sine. And if I factor the tangent in the second term, the only thing that is going to be remaining it's just the 1. Hold on. What happened here? Oh, this is equivalent to 0. I'm sorry. So now that we have it in this form, we can just solve each equation individually, because remember that's multiplication. So we have the tangent of x is equal to 0, and we also have the sine of x minus 1 is equal to 0. But notice that this expression, we have solved it a couple times before. We even did it on the first problem. Oh no, sorry, that's cotangent. Sorry, my bad. Let's actually come back to here. Where is my tangent equivalent to 0? Well, again, one way to see it is tangent, that's sine over cosine. So it is sufficient just to see where is my sine equivalent to 0. So let's take a look at it in here. Notice that at 0 degrees, my sine is 0. So, but instead of calling it 0 degrees, I'm going to call it 2 pi. Let me actually, the thing I did like an extra, yep, nope. There it is. It's just 2 pi. And where else is my sine equivalent to 0? Also at pi. Because there's at the sine of 180, that's equivalent to 0. So that's just pi. So for my first function, I got two possible solutions, 2 pi and pi. If I take a look at the one on the right-hand side, again, I want to solve for it. Let me isolate the function. So at this one, we're just looking for where in my unit circle the sine is equivalent to 1. And notice that that's equivalent at pi over 2. Because now we can see that the sine is 1. And that's about it. That's the only place where the sine is equivalent to 1/2. So let's just summarize this. So my possible solutions is that x is 2 pi, pi, and pi over 2. All right, let's take a look at one more example before we go. Same idea. I want to see, can I set it equal to 0? So let me set it equal to 0 by just adding a 1. But notice that here, I'm just going to also rewrite it. I'm going to write it in standard form, because I can just rearrange this expression to just be 2 sine of x, 2 sine squared, plus 3 sine plus 1 equal to 0. So I added a 1 and I wrote it in standard form, because now I can kind of treat this function like if it was a trinomial as well. Because I can treat this function like if it was just 2x squared plus 3x plus 1. Imagine that you want to solve this function. The only difference here is that instead of an x, I have a sine. But notice that the coefficients the amount of terms are all the same. So I can kind of think of this problem like if I would have wanted to solve this. And notice that that's a trinomial whose highest degree is 2, so I can definitely factor this out. And if we were to factor this out, we could have factored this function as just 2x plus 1 times x plus 1. Okay, and I convince yourself that if you distribute 2x times x, that's 2x squared, 2x times 1, that's 2x, plus x, that's 3x, and 1 times 1, that's just 1. So notice that this expression, we're able to just factor it out this way. So perhaps, coming back to the problem that we wanted to solve initially, I can factor the same expression, but instead of writing in terms of x, I can just write in terms of sine. So I can factor this expression as just 2 sine of x plus 1 as my first term times sine of x plus 1 as my second term. And now that I have two terms and they're multiplying and they're equal to 1, I can just solve for each one individually. All right, so let's solve the equation on the left-hand side. Let's isolate the function. Let's isolate the sign. So now that we have properly isolated the sine function, we're going to be looking at a unit circle. And we want to see under what values, under what degrees is my sine going to be equivalent to negative 1/2. Well, notice that here on the 210 degrees, my sine function is negative 1/2. So one of my solutions is going to be 7 pi over 6. And is that the only place where my sine is equivalent to negative 1/2? Well, that's not the case, because also at 330, notice that my sine is 1/2. So my second solution is going to be 11 pi over 6. So there it is. Those are the solutions coming from the first equation. So now let's solve the second equation. So isolate the function. And again, oh, that's minus 1, sorry. We want to find angles that if I take the sine of it, it's equivalent to negative 1. So let's look for, in our unit circle, where is my sine function equivalent to negative 1? Well, that's only one angle, and that is 270. So one of my solutions is going to be 3 pi over 2. So now, if we put them all together, then we can say that my solutions are equivalent to when x is 7 pi over 6, 11 pi over 6, and 3 pi over 2.